Hey PChem, today we're going to review some properties of water, why it is the way it is, and also aqueous solutions, which are solutions made with water. So first, really important thing to talk about is the structure of water. Water is made up of one oxygen bound to two hydrogen atoms. It looks a little bit like a Mickey Mouse face. One thing that this image doesn't show are two lone pairs of electrons. So if you remember how to draw Lewis structures, if we count the valence electrons of oxygen and hydrogen, add them together, we get 6 plus 2, 1 for each hydrogen, which is 8. So 2 electrons go here to make a bond between hydrogen and oxygen, 2 go here between this hydrogen and oxygen, and we still have 4 left, because 2, 4, 8 minus 4 is 4. So that means that we have to give oxygen the remaining valence electrons. So hydrogen can only hold a max of 2 electrons. Oxygen can hold up to 8 to achieve its octet. So that would be 2, 4, 6, 8 there, and then 2 and 2 associated with each hydrogen. So those lone pairs of electrons repulse one another because they are all negatively charged. So due to the Vesper theory, water molecules have a tetrahedral bent shape, and their bond angles between these two hydrogens, this angle here, is about 109.5 degrees, a little bit less, because they are pushed away by those other electrons around oxygen. Because it is bent, a bent molecular geometry has an asymmetric shape, which is kind of hard to grasp if you're thinking in 2 dimensions, because 2-dimensionally, this looks pretty symmetrical. You have a hydrogen, oxygen in the middle. But 3-dimensionally, it is not symmetrical. So because it's an asymmetric shape, and oxygen is more electronegative than hydrogen, we have polar bonds, and that combination makes the molecule as a whole polar. Oxygen carries a partial negative charge because it has high electronegativity and those lone pair of electrons, and hydrogen has a relatively positive pole. So this little lowercase delta, that means like partial, so it's a partial positive end and a partial negative end. And that polarity and structure explains a lot of the properties that we see in water. So we do want to talk about intermolecular forces again. Talked about this a little bit with the different states of matter. But one that's really important that is in water is hydrogen bonding. And I hate the name hydrogen bonding. I have a whole slide on it in the next slide. But hydrogen bonding is a type of dipole-dipole force, which dipole-dipole is a type of IMF, intermolecular force. So that means that when we have 2 molecules that are dipoles, so for example 2 water molecules, both of them are dipoles, the partial negative end is attracted to the partial positive end, and vice versa. So opposites attract. And so this dotted line here represents the intermolecular forces, the dipole-dipole force. Not all dipole-dipole forces are hydrogen bonds, but there are special cases where we have like a subcategory of dipole-dipole called hydrogen bonding, and that is a very strong dipole-dipole force. So hydrogen bonding is present in water and other molecules as well, but typically it will occur when you have within a molecule a bond between hydrogen and oxygen, hydrogen and fluorine, hydrogen and nitrogen, or another really electronegative atom. So the high difference in electronegativity causes this hydrogen bonding to occur. But again, I hate the name hydrogen bonding because when you say hydrogen bond, what comes to mind is that bond between oxygen and hydrogen in one molecule. But hydrogen bonding is not in a molecule. It's an intermolecular force, which means it's between molecules. So it is the force between 2 molecules, not a bond within a molecule. So hydrogen bonding is not a real bond. Hate the name, don't know why it is the way it is, it's just one of those things. So sometime throughout the year you're gonna have that confusion. Everyone does, but just try to remember the term hydrogen bonding for intermolecular forces is still an intermolecular force. So it is between two molecules, not within a molecule. So polarity of water and hydrogen bonds are responsible for a lot of the characteristics that we see of water. The fact that water has a high surface tension, that's why those water bugs can like see across it, why you can float a paper clip on water even though it's more dense than water. And I believe I have a visual in the presentation about liquids, about surface tension, so you can reference that to explain why water has a high surface tension. Water also has a low vapor pressure because hydrogen bonding is so strong. Has a relatively high melting point, so we don't really think of water having a very high melting point, like we see it melt all the time. But for what it is, it's pretty high. So the fact that it's a covalent compound and not like a metal or something that we typically associate with high melting points. And also has a less dense solid state, which is unusual. Most solid states are more dense than their liquid states. Water, that's not so. So that's why water, solid water, ice, floats when you have a glass of water, and why the icebergs float in the ocean. Next, we're going to talk about solutions. When we say solution, we're talking about a homogeneous mixture or homogeneous mixture, doesn't matter how you say it. And solutions, one substance dissolves another. Solutions can be any state of matter. So there are solid solutions, like alloys, liquid solutions, which are typically what come to mind, and gaseous solutions like air. You also have solutions where one substance, the solute or solvent, is in one state of matter and the other is in another. So for example, Pepsi, that is a solution. Now, when we open up a can of Pepsi, we have the gases coming out of the solution. So the solution is disappearing basically, but under pressure, that gas is dissolved in the liquid. So that's an example of a solution that has two different states of matter. There are plenty out there. The solute is the substance that is dissolved, typically present in the smaller amount, and the solvent is the substance that does the dissolving. Water is called the universal solvent, even though that's not really true, but in labs typically we use distilled water to dissolve things like salts and stuff to make a solution. So an aqueous solution is one in which water is the solvent. Aqueous, aqua, means water. And the solutes, what is dissolved, we can look at it at an atomic level. Sometimes solutes are atoms as their smallest structure. Some solutes have molecules as their smallest structure, and some have ions as their smallest structure. So for the dissolving process, substances that are polar or ionic can be dissolved in water. Substances that are nonpolar, like grease, fat, oil, things like that, cannot be dissolved in water. And later on, we're going to be talking about this concept of likes dissolve likes, which have to do with intermolecular forces. So the idea is that things with similar intermolecular forces dissolve one another. So dissolving is a physical change, not really a chemical change, although there is some gray area there. For example, when salt dissolves in water, ionic bonds are broken, which is technically a chemical change, but ion dipole forces are established between the ions and water molecules. So the dipole, the water molecules, are attracted to ions. The positive side of the dipole is attracted to negative ions. The negative side of the dipole is attracted to positive ions. For ionic compounds, this change is typically energetically favorable, so that's why we see the dissolving process. For nonpolar compounds, there are IMFs present within the nonpolar compound, and the IMFs that would establish if we were to dissolve that compound are less energetically favored, which is why we don't see it happen. So they're weaker, so it doesn't happen. Not all particles that dissolve are ionic, and some ionic particles don't dissolve very much. So table sugar does dissolve, but unlike table salt, it doesn't split into ions. It splits into small molecules. So those small molecules are surrounded by water molecules. Water interrupts the intermolecular forces between sugar molecules, and establish intermolecular forces with sugar molecules. So they kind of like block sugar molecules from one another. For the dissolving process, if we were to show it as a chemical equation, usually we don't say like this solid plus water yields this aqueous solution. We just have solid to aqueous, and that water is implied in the equation. So if you see something like this, that is the chemical reaction for the dissolving process. Electrolytes are substances that, when dissolved or melted, so when they're in some sort of liquid state, they can conduct electricity. So table salt is a good example. Non-electrolytes are those that do not conduct electricity, even if they're melted or dissolved, so sugar. So to conduct electricity, what happens is you have to have charged particles that are able to freely flow. So those charged particles can either be electrons, like we see in metals, or they can be ions, like we see in ionic compounds. Non-electrolytes do not have those free-flowing electrons or free-flowing ions, so they do not conduct electricity. All salts are electrolytes, even ones that are insoluble. So even if you can't dissolve it in water, that's what insoluble means. If you were to melt that salt, it would conduct electricity, which is why it's an electrolyte. Electrolytes are really important in the human body. That's why things like Gatorade, Powerade, they advertise electrolytes. Use them for pretty much everything. Your nervous system really needs electrolytes. That's how your muscles work. If you have low electrolytes, usually you get muscle cramping. Strong electrolytes are ones that break up almost completely. So salts with high solubility, meaning they break up in water easily, and strong acids and strong bases, which would also break up into ions in water. Weak electrolytes are ones that don't break up very much. They're insoluble salts, and weak acids and weak bases. So insoluble or low solubility means it breaks up, but not very much. Technically, everything is a little bit soluble, so there's no such thing as completely 100% insoluble. But if there's low solubility, we have a weak electrolyte, doesn't conduct much electricity. And again, weak acids and bases, they don't break up very much into ions. So it's again a weak electrolyte, not much electricity flows. Okay, so that is it for this presentation on water and aqueous solutions. Let me know if you have any questions.